Welcome back to part 2 of section 4.3. We're working on finding those open intervals on which a function is increasing or decreasing. Right? So I've got my function here. I'm going to do the same thing I did last time. Right? I'm looking at a quartic equation with a positive leading coefficient. So those can look like this, which means we'd have a couple of intervals, an increasing and an increasing, a decreasing and a decreasing, so maybe 3 critical numbers possibly we could be looking for. All right, so first things first, to find those critical numbers I need that derivative. So what is my first derivative? Looks like I'm looking at 4x cubed minus 6x squared, and then I'm going to find my critical numbers. Are there any of the does not exist type? Well, that is a polynomial that has no issues, so there are none of the does not exist. Now I'll look for when is f prime equal to 0. So when is 4x cubed minus 6x squared equal to 0? Let's see, I'll factor that thing. I think I can get a 2x squared out of it times 2x minus 3 equals 0. Okay. That one tells me I have a critical number at 0. Technically, it's a double root. And this one tells me I have a critical number at 3/2. Now, you might be wondering what's going on here, because over here, we said we were looking for 3 critical numbers, and down here, we've only got 2. Well, this was just a generalized statement that quartics sometimes look like this, but they don't have to. And if you want to get fancy about it, there actually are 3 critical numbers there. This is a double root because it's squared. Okay. All right, so now what do I need to do? Oh, okay, so now I need to figure out what's going on here. I've got a critical number at 0. I've got a critical number at 3/2. That's going to give me 3 intervals that I need to test. I'll test interval number 1 first. I need a number from interval number 1. I'm going to pick the value of -1. And I'm going to find the value of the first derivative at -1. Four times -1 cubed is -4. -6 times -1 squared is -6. So over there we are less than 0. So on that first interval, f prime is less than 0. Now I'll pick a number from interval number 2. I'm going to choose 1. Wait, I wanted to change to green. I'm going to choose 1. Right? And then I'll find the value of the first derivative when x is 1. So that's going to be 4 times 1 cubed minus 6 times 1 squared. That's going to be -2. So on that interval, we are also decreasing. Okay, now we'll check interval number 3. I need a number on interval number 3. I'm going to use 2. And I will find the value of the derivative when x is 2. Let's see, f prime of 2 is going to be, what's that going to be? 4 times 2 cubed minus 6 times 2 squared. 2 cubed is 8. 8 times 4, 32. 2 squared, 4. 6 times 4, 24. Minus 24. That's going to be a positive number. Greater than 0. Now you notice I didn't even figure out what this is because I don't care what the actual value is. I just need to know whether it's positive or negative. That's positive, so I'm positive on that interval. Right? The last step now is to wrap it up and make it look pretty, to give the final answer. So where are we increasing? Okay. Well, we're increasing on interval number 3, which starts at 3/2 and goes on forever. And then where are we decreasing? Well, now here's where things get tricky. We're actually decreasing on interval number 1 and also on interval number 2. Okay, so decreasing is where it gets tricky because it's decreasing on interval 1 and interval number 2. Now, interval number 1 is from -infinity to 0, and then union with interval number 2, which is 0 to 3/2. Now, here's where things get weird. Sometimes, depending on the author and depending on the homework, If you have two intervals of the same nature, that is, they're both increasing or both decreasing, that are butted up against each other like this, that only differ because of that critical number, sometimes you'll see people do this and take it all the way up to 3/2 and just say it's increasing on the, or it's decreasing on that entire interval, so decreasing in this case. Now, I'm not a big fan of doing it that way. I prefer to separate the two intervals out, and I believe that Larson, the author of this textbook, does it that way too. But if you're working on a homework problem and you get something like this, and they tell you you're wrong for having two intervals, maybe try one interval. The reason I can't give you a definitive answer on which way to do it is the homework isn't always written by the same author, and sometimes they might have an author write the homework who wants this, and sometimes they might have this. So just bear in mind that that's a possibility. Okay? All right, so one last thing, a phrase that you might run across is the phrase strictly monotonic. A function is said to be strictly monotonic if it is either increasing or decreasing, and that's it. So nothing we've looked at so far would be a strictly monotonic function because they've always changed. But if you had something that maybe did something like this, then we could say that that function is strictly monotonic because it's always an increasing function. Okay? Or if you had a function that was always decreasing, then you could say it's strictly monotonic because strictly monotonic is just a fancy way of saying on the interval that we care about, that entire interval only has one behavior. Okay? Now be careful with this one because sometimes they can do tricky things like this. You might have a function whose global behavior is this, but if all we care about is some little tiny piece of that, then that function would be strictly monotonic on the interval AB because it is only decreasing on that entire interval A to B. So if all we cared about was A to B, you could argue that it is strictly monotonic on that interval because that's all we got there. Okay? So just be careful with that because you have to make sure you know what it is, what's the interval that they're asking you about. Okay? All right, moving along. So this is going to bring us to something called the first derivative test, where we're going to take the idea that we've used already, that increasing and decreasing business, and use it to figure out where maximums and where minimums are, where extrema are. Okay? So once you figured out whether the thing is increasing or decreasing, that leap to finding the extrema isn't that bad. Okay? Now, if you remember, we looked at this function earlier. This is the first one we looked at. We found the intervals of increasing and decreasing for the function x cubed minus 3/2 x squared. And we found that it was increasing on the interval, and this was this problem right back here from video number 1. We found that it was increasing on 2 intervals and decreasing on 1 interval. It was increasing on 2 intervals and decreasing on 1 interval. Okay? Now, if I have a function that is increasing and then at a critical number switches to decreasing, I'm talking about right here, if I have a function that is increasing and then switches to decreasing, basically what I've said is it goes up and then it goes down. Well, if a function goes up and then goes down, it must have passed through some sort of a maximum. So if you have a function that is increasing and decreasing, and this change is at a critical number that is in the domain of the function, you've found a maximum. The exact reverse is true for a minimum. If you have a function that is decreasing and then increasing, and that critical number is included in the domain of the function, if you went down and then you went up, you found a minimum. But remember from the section on maxes and mins, the increasing and decreasing only gave us the x values where these things occur, those critical numbers. To get those y values, we have to go back and plug into the original function. That is f of 0 right there, and that is f of 1/2 right there. Okay? All right. This brings us to the first derivative test. The first derivative test said, let C be a critical number of a function f. That means that it is a derivative is equal to 0 or the derivative doesn't exist. And that f is continuous on the interval that contains that critical number. If f is differentiable on that interval, except possibly at c, then f of c can be classified as one of the following. If the derivative changes from negative to positive, down to up, decreasing to increasing, what are you looking at? Well, then you're looking at a relative minimum. Okay? If f prime changes from positive to negative, that means it goes from up to down, then we're looking at a maximum. Now, if f prime is positive on both sides or negative on both sides, then we're looking at absolutely nothing. All right, so let's take a look at some examples down here so we can pair them up. This picture right here, I've got a critical number. I've got a decreasing to the left of it and increasing to the right of it. That means I went down and then I went up. That means I'm looking at a minimum. That's number 1 right there. F prime changed from negative to positive at that critical number. Okay? Let's look at this graph now. Okay? I've got a critical number C. To the left of it, my derivative is positive, which means I'm increasing. To the right of it, my derivative is negative, which means I'm decreasing. So that means I've got a maximum. That's number 2 right here. Okay? These two graphs down here are number 3. This is where you have a critical number, but to the left of it you're increasing and to the right of it you're increasing. And if to the left and to the right you're increasing, you went up and then you stalled for a second at that critical number and then you went up some more, that's not a max nor a min, right? Similarly, over here, critical number, I was decreasing and then I'm still decreasing. That's neither a max nor a min either. That's just I went down, I stopped going down for a second, and then I went down some more. Okay? While those last two happen, it's these two right here that we care the most about, because those two right there are what's going to give us our maxes and our mins, our maximum values and our minimum values that we're looking for. So just to review, when is it a minimum? It's a minimum when you have a critical number, derivative to the left is negative, decreasing, derivative to the right is positive, increasing. It is a maximum when you have a critical number. Derivative to the left is increasing, derivative to the right is decreasing. Then we have a maximum. Be careful though, because it is very, very easy to get a problem wrong. And I want to just make a little sketch over here to the side to show you what I'm talking about. If this was my original function, y equals 1 over x squared. Over here on the left, it's an increasing function. Over here on the right, it's a decreasing function. And c equals 0 is a critical number, but it is neither a maximum nor is it a minimum because it is not on the graph. All of this talk over here about maxes and mins required that these points associated with C, that is the f of c here and the f of c here, that those points are on the graph. If the point isn't on the graph, it can't be a maximum, nor can it be a minimum. It has to be on the graph first to say it's a high point or a low point. Okay? All right, we're at 14 minutes right here. I don't want to start this example with just a couple minutes left, so I'm going to stop the video here, come back and make a part 3, and that'll be where we'll start. We'll find the relative extrema of this function on an interval.